I'll suggest people, please feel free to go get the coffee and all while the talk is going on, and we will try to reduce the break a little bit so that we can recover. I know some of you have travel plans and all, so we'll try to dynamically adjust. So Sameh, he will be talking about high performance federated and distributed modeling of spatial data at scale. He's at KAUST, Saudi Arabia. He's talking from there. So he got his MS and PhD degrees from the Ohio State University in 2014 and 2016. He is currently a senior research scientist at the Extreme Computing Research Center at KAUST. His research interests span high-performance computing, applications, big data analytics, climate weather modeling, large-scale spatial data sets, parallel spatial statistics, algorithm-based fault tolerance, and machine learning and data mining algorithms. He was a member of the KAUST team, nominated for the ECM Gordon Bell Prize in 2022, and awarded the prize in 2024 also under the climate track. For their contributions to large-scale climate and weather modeling and prediction. So he actually contributed to MUG in the previous years. This year he couldn't travel, so we are trying to bring him through online. So let's give a big welcome to Sameh.
Thank you so much. Can you hear me?
Yes, yes. Yeah, you can share
your... So thank you for inviting me. So for my presentation, I will have something a little bit different here, but somehow connected to what Jeff just presented to us. So my name is Sameh Abdulah. I'm working as a senior research scientist at KAUST. Today I will present our recent work about high performance federated and distributed modeling of spatial data at scale. Okay, you can see two slides, right? Not one?
Not yet. Slides are not coming.
So you can see one slide or two slides together?
Nothing. We just see you.
No slides, Sameh.
Okay, let me share first. Okay.
Yeah, I think. Yeah, now we see. You can go to the presentation mode.
Yeah, now it's good?
Yes, good.
Yeah.
Yes.
It's good that we discovered this early. Okay, so I just here will give an introduction about what we are working on at KAUST, or me working on at KAUST from 2018 until 2024. Actually, our main objective during more than 6 years was to develop a spatial statistics application that can scale on supercomputer, GPUs, CPUs, and to be able to model a very large number of observation on climate weather application. So this is to explain our problem. Assume that we have, for example, a lot of sensors distributed over the globe, and it's, for example, read something like the temperature, and we need to build a spatial statistics model that can capture the features of those locations and find something that we can use later for prediction in spatial, or even prediction or doing forecasting on the future. And for these 6 years, we actually built ExaGeStar, the software. So the main point here is to collect all the data that you have, put it on one big covariance matrix. So if you have 1 million location, you need to build a 1 million by 1 million covariance matrix. Then using parallel linear algebra, you can scale this on supercomputers to reach to the point of prediction and kriging. And we did a lot of improvement to the linear algebra part related to use GPU accelerators, tile algorithms, using mixed precision on GPUs, and low rank approximation. So the point here that we can collect all the data on one place, build this very big covariance matrix, and start do the whole work using linear algebra on supercomputer. However, However, actually the spatial data from the beginning, the nature of spatial data, it's already distributed. So it's not on one place. And even if you bring all of them on one place, you need to find maybe a more smart way to model these data rather than building a very, very big covariance matrix and start to deal with. So first, the spatial data already distributed. It's cross sites in many cases. And this means that you need to move a lot of raw data from one place to another place. So to reduce this a little bit, for the literature and statistics, there is many ways to reduce the amount of data that you need to move by doing a kind of compression, statistical compression, like low rank approximation or VK approximation. Those kind of things that can compress the data for you. At the same time, since you already have those data on different regions, you can do a decentralized modeling. So you don't need to model all the data together. You can model the data on the site that's already collected from, and at the same time trying to send and receive some very small summary about these data so that you can still keep the global model feature that you are looking for. And when we talk about one system, here MPI can appear because you need to do almost a set of functions that close to what you are doing with machine learning, because the modeling, it's an optimization problem where you are on each step, you are doing a function, a log likelihood function, and you need to all reduce the parameter between all the processing unit that you have. So the core idea here is, okay, since we have the data already locally, we don't need to gather all of them and build this very big matrix. If we have 1 million locations, we don't need to build 1 million by 1 million matrix to do the modeling. Let's model data locally. For example, having 100 matrices, each is 10K by 10K. It's easy to compute, but still you need to find a way to keep the feature of the global model, and this is the big problem. So the environmental data in general is naturally distributed. As I said, temperature, humidity, everything is coming from, for example, from sensors that are already distributed on some region, coming from satellites, coming from a sensor network, coming from some institutes. And your main target is to model these data by first gathering them on the same space, at the same place, and start to deal with them. But you will have a problem related to bandwidth, latency, and also in some cases, maybe it's not related to environmental data, but also the idea of spatial modeling can be applied to healthcare sector, many other sectors that need privacy. So I have the data, I will not give it to you. I just can share with you some information if you need. And you need to build this global model. And this main problem starts on the machine learning community. Then they have this federated learning track. And now we are trying to investigate the same on the spatial modeling by doing federated spatial modeling. Also, you will have a problem with the scaling, because if you have more observations, you have more location, this means that you are squaring your problem, n square on the memory storage and n cube on the operation part. So now we need to design something. Our design principle need that, okay, I need to compute near the data. I don't need to move the data here and there. And I don't need to exchange everything. I just need to exchange a small information that can keep the global model as it is, okay? At the same time, we added this federated principle. Okay, since you all do compute your data locally, try to not share your data with anyone because of the sensitivity of data. So we also need to keep the raw observation and communicate only what the model needs. There is a lot of statistical proof here and equation. I will try to just, for this talk, I will try just to capture what exactly we need. So usually when you do the modeling, you are doing the modeling on a specific location S. And you have three main parts of the equation. Deterministic part, and the spatial structure, and the noise. So For the covariate, it's not a big deal because it's deterministic and you can do it locally for the local data that you have. And you just need to share this gamma with other processing unit or with other source of computing that you have. For the noise, the same thing. You just need to share this on every step. So you are doing an optimization problem. Every step, I need to send gamma to everyone. I need to send the noise that I have on my local data on everyone. Our main problem is the spatial structure, because the spatial structure depend on having a correlation between all the data that you have. If you start to just model in your local data, this means that you are losing the correlation with the data on other regions. And this is a big problem because now the global model will not be that efficient anymore. So we need to find a way so that we can keep the spatial structure and having it shared between all the points while keeping the data locally without sharing the data itself. So I will, to make it more related to our workshop here, so I will deal with the region here as an MPI rank. So let's assume that I have an MPI rank. I have an MPI node. This MPI node has some of the data, and it will start doing a local modeling. So I need to understand what exactly this MPI need to share with other MPI ranks. And at the same time, I want to be sure that I keep the global model quality at the end. So the two simple way is first is to do what we call naive independent model. Okay, let's forget about sharing anything with anyone. Each MPI process will do the work on its local data, and I will just take a summation of the log likelihood value that I have at the end. But of course, you will have now a fully separable model. You will do easy thing, but at the same time, you will lose a lot of global features and correlation between different set of data. Or to do full Gaussian process, and this is the normal way, is to, okay, let's communicate all MPI process, send all the data to each other. We know the data, and we build this covariance matrix globally, and we try to solve it together. And this is another solution. But as I said, it has problem related to scale and related to bandwidth and latency. So the statistics solution, or the statistical solution that we publish on one of the statistical journal is, okay, we have a way here. We have something called latent spatial base. This latent spatial base, or latent vector, eta, this latent vector is a statistical way that can capture the correlation of the spatial field, the whole spatial field, on one small vector. And this small vector can be shared between all the MPI processes that you have. I will not go in details on this, but you can assume that all the covariance matrix that you have, you can replace it by this small vector. And this small vector can be updated on each iterations so that each process will know the new values inside this vector, and it can update its parameter based on that. So this eta is one of the parameters that we need to do, but to compute this eta, and again, this is very statistical slide or statistic slide, then I will just simplify it. To compute this eta, we need to compute on each step 5 different vectors: mu, sigma, and gamma, and the noise, and theta, which is the parameter that we are looking for. In this case, using just this trick, the low rank trick and the LPO reformulation of the log likelihood value, each MPI process can start to compute all the information it has on the local data on the first step, on the first optimization iteration, then shared with others, or with this central server, or with some of the MPI, other MPI processes. I will explain this in a minute. Share those 5 vectors. Then, based on those 5 vectors, there is a decision that will be taken and distributed again to the MPI processes. Then all the MPI processes can update their own theta, okay, which is the global theta, which is the main thing that we are looking for on the statistical problem. So the thing is this, we have local kernel, we will distribute, or we will compute some small summaries related to those 5 local parameters. Then we will do reduction. So we will have a global theta that all the MPI processes should know about and start to update their model. So to explain each of those, we have first this mu and sigma, which compute the eta, the latent vector that we are using for correlation definition. We have this regression update that update the latent quantities that we have, and we have the noise and the covariance parameter. Just because I didn't mention this at the beginning, if we are looking to the normal MLE or the modeling operation, the main idea is to do the model and retrieve theta vector, which is a set of parameters that can explain or describe the spatial domain. Then you can use this for the prediction. So from the beginning, this is our main target during the optimization problem of the spatial modeling. However, now we have those new 4 parameters just to share the spatial structure between all the MPI nodes, and local sigma for each local data, and the global sigma for the whole data. And this is our main target. So now our MPI execution pattern will be like that. MPI process will compute, aggregate, then update the parameter. Then we will go to the next iteration, 3rd iteration, 4th iteration, until the convergence of the global model. This statistical theory has been proved on one of our paper, and it works very well to do this distribution. So this is a good idea, but now let's see how we can share the data or share the information between the nodes. We have different strategy. First thing is to have a central server. So at the central node, a master node. So all the local node will send to this master node and start to deal with. Or we can just share the information that we have with the neighbors. Or we can have a totally decentralized framework where all the nodes need to send all these weights or all these vectors between all the nodes that we have. So we have different topology of how we will distribute the data and how we have the data shared between the nodes. And if you will not send the data to all the nodes, so maybe it's enough to do MPI I send and I receive with your neighbor, for example, or what you are picking here. So this different strategy will give you different statistical error on each step. And this is also a very important point. So if I shared my data with all the points that I have, this will be all the MPI process that's available. This would be good. But if you have some of them, you are reducing the communication, but at the same time, you are injecting some statistical error to the story. So let's have a very simple MPI code here to understand what's going on. So each MPI process need to do a local summary, then start to exchange the summary it has, again, in different scenarios, then update the parameter block. The different scenarios of doing this summary, reducing summary, exchange summary, may be or reduce if we have a global summary with all the nodes, or just reduce if we have a centralized server, I send, I receive. So based on the topology that you are building for your application, you will have different MPI primitives that you are relying on. And this is again a summary, which will give us to the question that I have here. So if you have different strategy, you will depend on a different MPI function. And of course, you will have some challenges. MPI reduce, for example, you will have a problem with the collective latency. If you have MPI neighbor all together, you will have a problem with your topology and how to build it. And the point here is, based on this new structure, can we build an MPI communication schedules that could design with the hardware topology and the statistical mixing and conversion rate or not? So the main idea of having this framework that it's impacted by the statistical error It's impacted by the topology. It's impacted by the distribution of the data on different nodes, because also we have heterogeneity, system heterogeneity, and data heterogeneity examples or cases with the federated modeling. So can we build a co-design that can help connecting the three together, the MPI, the hardware topology, and the conversion rate, so that we can reach to the best time to solution and the best communication cost or not? And this is, again, I will mention what Jeff said. Maybe one of the things that we can do with the AI is to do or debug MPI library or do something from scratch. But at the same time, we can generate a lot of code, and we can go to the direction of co-design implementation instead of implementing each layer from the hardware to the application as a standalone layer. So building things together, AI can help us to do this. And at the same time, we can control the capabilities of each MPI function based on the application, not just to do a general thing. So the problem didn't end. So our framework is not the problem. Our framework is just because we have this kind of topology or different topology. No, actually we extended this to what we call asynchronous federated model. Let's assume this case. You have several MPI processes, each is doing something local. Some of them has a lot of data. They are very late to send their update. Others, if we are dealing with synchronous execution, others MPI process are waiting for this MPI process to finish the work. And this is actually some cost or overhead that add to the pipeline, the full pipeline of the application. So can we actually do asynchronous execution? How is that? Can, if just 4 or 5 MPI process finish the work, can they do this iteration, go to the next step, and other MPI process can just join on some of the iteration? Yes, actually we also proved this theoretically, and we built some statistical algorithm can handle these cases. So in this case, you can do asynchronous execution, but at the same time, if you will include MPI on this, so you will do MPI I send, MPI I receive, you will wait until you receive an amount of work or data exchange that you think it's enough to go to the next step. How can I know that the amount of data exchange between the MPI process is enough to go to the next iteration? By computing something called statistical error. Okay, the statistical error or stillness can understand the amount of error that can be okay to go to the next step. Okay, but MPI will not understand this. So MPI will I send, I receive, and I will give, for example, if 4 or 5 messages I can see, I can jump to the next iterations. But this will depend on the data itself. So if we go back to this co-design idea, now the MPI can understand when exactly I can skip, when exactly it's enough for this iteration and I can go to the next iteration. If the MPI can understand statistics, can understand the error, and can measure if this error is enough or not for the stability of the framework. So again, we go to the step of MPI co-design with the application itself. So those are the solution, statistical solution that we put, and we build it already using the MPI. But we think that if MPI also can understand this, maybe this will help us to reduce the cost. So this is the asynchronous aggregation. Now with your MPI, you can do I receive, and you can wait until you receive an amount of messages exchange between different MPI processes. Then you can start to do the update. So this is the normal way to do things with the current MPI library. So if you are very interested on understanding the statistical foundation of this work, which I don't think so with you guys, you can go to our GRSS, Journal of Royal Statistical Society, to understand things. And if you are caring more about the asynchronous modeling and how it works, you can go to this archived paper. However, we are now doing one more paper. Still, maybe it will be on archive in 1 or 2 weeks to give some idea about how to implement an HPC version of this work. But also with these two papers, you can find some primitive MPI graphs and experiments of different features and theory that we proved statistically, and we practically tested it using MPI. So why we need all of that? So you guys built ExegeStat 4 years ago doing this modeling, again, because the data itself, for example, on some cases like air quality and climate change is already distributed. We are now at KAUST, we are moving to something called transitional research, where we are trying to apply our solution to the government and also to the industry partners. And when we move to those partners, we found that we need a robust frameworks. We need maybe to reach to a certain point where we can do a real-time modeling and prediction related, for example, to air pollution, instead of waiting for 1 or 2 hours to have updates about the current situation of air pollution in your region. We need a real-time modeling, real-time prediction, and we cannot reach to this without HPC and without reducing the communication cost, and also reduce the computing cost by distributing the data to a certain level. So to summarize here about why this is important for MPI community, again, this is related to build this MPI co-design with the application. We care about minimizing the network cost, and also this can be happen by relying on understanding the statistical error more than understanding the computing behavior. Also, statistical adaptive communication by communicating when needed. So we will not have fixed amount of communication for each iteration. I will just communicate until I understand as an MPI, I understand that, okay, this is enough from the statistical perspective, and let's go to the next step. And actually, when I wrote these statements, I was also thinking about machine learning. So with machine learning, also you are blindly training. I will go train until I reach to this threshold. This is enough. Let's then stop here. However, if I can, even during the training, understand the error that I'm adding or reducing, I can change during the training itself, and I can be more smart on the conversion point that I can stop to. So you may iterate or train for 1,000 iteration, while 200 is enough. So you cannot understand this until you try it. But actually, you can understand this, or there is one layer of the software stack can understand where exactly I can stop. Then I can finish my training. Okay. Also, some other points related to the sparsity of the region, also about fault-aware statistical inference. So what if I have this MPI process already killed? We have a mechanism to continue our modeling, or continue our optimization problem, but also this is very important for MPIs to not stop. Just understand that it's okay. We lost this, it's okay. I can continue until I can recover things. So you don't need here to depend on fault tolerance algorithm. You just need to explain to MPI that it's okay, go ahead. Then also we can have this GPU resident distributed inference, so you can have a compact low rank summary during the execution. You can also have, more than looking for time to solution, you can also look to pi to converge, energy, joules to converge, dollar to converge. So you can have different metrics about your application rather than, okay, I need to do 100 iteration and I just need to reduce the execution time. So the takeaway here is to go from just MPI supporting application to MPI co-design to understand the application itself, understand the needs of the application, and help to implement some of the algorithms on the application layer. So we need to build this. This is just one application for the spatial statistics application. We need to keep this federations, which can help to keep the privacy of the data. Also, low rank and the small amount of data that can be moved this is better than building this covariance matrix. Of course, when we talk about distributed work, we need decentralized algorithm, we need asynchronous algorithm, and we need help from the MPI layer to do this asynchronous communication on a very efficient way. Also, based on the topology and how you are distributing your data, this also will impact about the collective or the communication that you will do. So this is one of the perspective. I think it's very important to the workshop here. So I think the next frontier with the AI, with the easy way to build MPI, is to do MPI or co-design MPI with the hardware and with the application, not just to build an MPI library that can be stand for different application, but we can have a customized MPI function for each application. Thank you so much.
Let's give thanks to Sameh. Any questions for him? Locally or online? Yes, Pankaj, let's unmute him and he can ask.
Yeah, DK, thanks. And great talk, Sameh. I have a question. When, at least my experience with weather codes, you end up doing things like Legendre transforms and Fourier transforms on the global variables. And even in the China talk this morning, you saw, some transpose operations that you have to do depending on longitudinal versus latitudinal ideas, right? So it's interesting to see that, you are taking a partitioning approach and that is transpose free, it appears. Okay. What is
it's not free, but less, yes.
What is the range of problems for which, you can't escape the transpose? And what about your problem made it possible to do this kind of localized processing?
Okay, I didn't say that we will skip it, but we will do it on small matrices. So you don't need to do a lot of work here because your data now is a small amount of data, okay? So you're still doing the same algorithm, but you are doing it on a small amount of data instead of this big amount of data. So for example, I will give an example to what we did on 2024. So we were able to, on the whole frontier, 37,000 GPUs, to do factorization and transpose for a matrix 32 million by 32 million matrix. So this is the number of observations that you have. You cannot go far until you have a bigger supercomputer. And actually, just the transpose took about, I think, 2 hours or something. And this is one part of the full pipeline of the application. However, you can distribute this and you can accommodate any number of measurements that you have. We tested the robustness of the new algorithm up to, as I remember, 200 centers, 200 places. So if you assume, for example, if each place has something like 10,000 measurements, so you can do the math here and see how large you can go. Of course, to be sure that this can scale, you need to scale the number of places or sites that you have. But unless this, we don't have any restriction, theoretical restriction about the amount of data that we can accommodate with this method. I don't know if this answers your question or not.
Just very quickly, I think, if you look at ocean currents and polar vortices and other global phenomena, it's not clear if, aside from the efficiency of the small matrix approach, whether you can actually detect phenomena that would have been detected through Fourier or other analysis on the global data reliably, especially, if there is like you're switching between time domain and frequency domain representations. So I was just trying to understand, how can you escape some of these curses like FFT and others, which require great data movement?
Yeah, okay. So we are just like those methods. So we are not using FFT here, okay? We are not converting from the spherical domain to the longitude and latitude domain. The likelihood method just depends on the longitude and latitude as it is as a spatial domain. Then we are building this covariance matrix and doing the transpose on it. Okay, but the full pipeline, because I know that this is maybe linked to our golden ball here in 2024. The full pipeline of doing Fourier transform and doing the spherical to longitude and latitude transform and the others, it's not a part of this project. So this is, yeah, it's not a part of this project. Okay.
Yeah, thanks, Pankaj. Thanks, Sameh, again. I think we need to move, might be a 10-minute short break. 11:15 we'll start. I think we'll recover at the lunchtime. Okay.
Thank you.
So,
thank you.
Thanks again, Sameh. And if anybody has question, please feel free to ask on the online, and we can continue. 11:15. So let's take a short break, and then we'll have your presentation.